Okay, this really is the last one. I know I said that last time, but I forgot about this part. Hopefully this one will be short enough where I can go trim the other one and tack some of it on here. I don't know. Normally we take like 2 months to do this unit. So I am going to use the glue ends for the 10.2 stuff. If you don't have them, it's not a big deal. You're going to be able to easily know what the question was. Oh, look at me. Do I have room to put them all on there? Maybe. Oh, they don't fit. Okay. So, okay. So light is this odd, both a wavelength and like a little package, a certain like specified amount. And it all has to do with wavelengths. So we'll start off with that. So to answer that question about, so why does it act like a wave? Why does it act like it's got like a certain amount or specific amount of light, of energy? It's because different wavelengths have different energy. So different lengths of waves so obviously that's wavelength, which is lambda, which looks like that. So different lengths of wavelengths, they have different energies. And so what we can do is, if we step out of this, well, how much energy does it have? Well, that depends on what wavelength it is. If we just step out of that and think about it independent of wavelength, so we're going to step out of thinking wavelength, okay? And instead, what we're going to think about is that you can have, if you're thinking about how much, there's a certain amount of energy that is classified as a photon. It's a certain package or parcel of light. So it's going to change depending on the wavelength, because wavelengths have different energies. But we can say that, so we can define, because that's where we're getting to here, a photon, which is funny because I think about, of course, y'all ever watch Star Trek, so what do you care? But they'll have like photon torpedoes, and they use these words like they mean something to them, and they don't mean anything to them like they mean to us. So a photon is this, and I don't know how y'all feel about this word, but it's a discrete or a known amount of light. So this is a known value packet of light. Technically, it's the amount of energy that I think for when you have a electron changes its orbit, but whatever, we're not going there. So that's the answer. So how does it behave as this distinct parcel or package of light? Because regardless of whether something's low energy or high energy, which means it would take more wavelengths if it's low energy to get to this known value, or it would take less wavelengths if it's high energy, we can still define a certain energy amount of light as a photon. Okay? That's independent of wavelength. But, so we want to think about it this way. If you've got a short wavelength, so it looks like this, but like that one, it equals more energy. So short, small, inversely proportional has more energy. So a longer wavelength something more like that has relatively, compared to the two, less energy. So to get a photon from this longer wavelength, you'd have to have it have more wavelengths, okay? Does that make sense? This also answers the relationship of energy and wavelength. The shorter, the more energy. The longer, the less energy. I think I'm going to move 3, so this is 1. 1 is saying, stop thinking of wavelength. We can give energy as an amount of, light as an amount of energy called a photon. And that's going to differ based on wavelength because, for number 2, shorter wavelengths, it would take less to get you to the same photon as it would take more for a longer wavelength. All right. So then we skip over to these properties of light. So 3 says, how come leaves are green? Why do we perceive leaves as green? You see what is reflected. So we see what wavelengths are reflected. So they're going to come back to you, to your eye. So here's your leaf. Here's your eyeball. Here's some eyelashes. And as light comes and hits the leaf, light is reflected, and that's how you see it. Okay? So visible light, we can't see all of it, is 380 nanometers, and it goes up to 750 nanometers. That's what you're able to see. And it falls in the spectrum according to this color. It goes purple to blue to green to yellow to red, lining up with the same. So let's see what we can say based on what we just wrote. Okay, here's what I'm going to say then. Every wavelength is a different color. So, different wavelength, different color. Well, I don't even know what that means. Like, how do you even get color out of a wavelength? Well, it has to do with pigment. So, there's different pigments. So these pigment molecules, now we had a really good talk, maybe you didn't think so, but I did, about how cool that the pigments are that are in the photosystems. So we see them as green, so they reflect that light back to our eye, but what they absorb, and then they get this resonation, is going to be the rest of the wavelengths. So pigment molecules reflect, that's what you see. So a certain wavelength, and they absorb or transmit, but we're going to go with absorb, other wavelengths. So, okay, I'm wearing a blue kind of jackety thing. Why is it blue? Because the pigment used in the cloth reflects blue back to our eyes, and it absorbs everything else. So we're going to make the statement again. What is reflected, and this is what wavelength is reflected, is what we see. And what's absorbed, so the wavelengths that are absorbed, can do work, because wavelengths have energy. Energy can do work. So now they ask me, not the big story of the world, but like I asked you why leaves are green. Okay, let me answer the question. So, getting to all this, chlorophyll, A and B, but it's a pigment. And what does it do? Well, that's why leaves are green. So that pigment reflects green wavelengths to our eye, and it's going to absorb the other wavelengths, which it does, though, it uses those to do work. It lets the energy resonate through the pigment molecule and kick the electrons out. So if that's the case, and it reflects green, it's going to absorb, so it absorbs that spectrum on this end, that purpley blue, so violet blue. It's going to reflect the green and the yellow, because that's what we see, and it's going to absorb red. That's what it does. So, what's absorbed can do work. The next question. Oh, so there's a spectrum, which just means something that starts at one value and it goes all the way to another, and you can measure all of it. So the absorption spectrum for chlorophyll A is, so let's go up here, this is 4. And since chlorophyll A is the main pigment, that's the one we're going with. So for chlorophyll A, it's going to absorb over in this purpley blue. Then we're going to have this gap of what it doesn't absorb because it reflects it, and then it'll be over here in the red. So you're going to get 400 to 450 nanometers. So that's over in that whole purpley blue. And it's going to go from 650 to 700. And the gap here in between is where the green would be. So it's going to do this purple-blue. Doesn't do a whole lot here because it's green. And then if you get to 650, then you're able to absorb in the red. So absorption has to do with what we can measure that the actual pigment absorbs. I know that sounds like a silly thing. However, so there's an absorption spectrum for photosynthesis, okay? And this is the one using just the pigment chlorophyll A. When you look at action spectrum means where does photosynthesis occur? Like the action of photosynthesis, what wavelengths cause photosynthesis. So let's write that. So the action spectrum of photosynthesis, what they're saying is what wavelengths cause photosynthesis to happen, to occur. Well, it's got to be this, right? 4 to 450, 650 to 700? Actually, no. The action spectrum, so this is where photosynthesis actually occurs, is bigger than that. Yes, it's at 400, but you get photosynthesis all the way into 530. What? Really? Like past where that chlorophyll A works? Yes. And even though there is a gap here, it starts earlier also. It's from 600 to 700 nanometers. Well, that makes no sense. Yeah, it does. It just means that the action is the result of chlorophyll A and something else. Something that can absorb past 450, something that can absorb before 650. So this is a question they ask. The action spectrum of photosynthesis is greater than, okay, the absorption spectrum of, and it's done by pigment, of any one pigment. And the reason is because it's a summation. So what happens is it's a summation of chlorophyll A, I got that up here, plus B, plus what's called the carotenoids. The more like orangey looking stuff. So these are called, right here, are called accessory pigments, and we talked about those. We looked at that really old video from the 80s, and it was saying that these absorb energy, and they hand that energy off to the photosystem to make it to where that they're contributing. So they're like the little contributors, and this is the main guy. So why do you have these accessory pigments? Okay, accessory pigments, which is not just the carotenoids, that's going to be also chlorophyll B. They contribute to and expand the wavelengths that photosynthesis can actually occur at. So they're going to expand the wavelengths that photosynthesis occurs, which means they expand the action spectrum. The other thing that they do is they have this protective ability. So that way that light isn't just energy hitting these molecules. If they absorb it and use it to do work, they're doing good with it. So they're going to expand that, and then they're also going to be what's called photoprotective. And that's going to be because they absorb light that could damage. Because it's energy. Okay? So the last is, describe what occurs when a molecule absorbs a photon of light. Okay, so this is what I was going with before. So if we get into, you said it was a measurable, known value packet of light. So a photon of light is equal to, this means change, right? Delta, change. So the change in potential energy of electrons, or an electron moving to a higher, different orbital. Does that make sense? So this whole piece here, which is being photoprotective, all you have to think about is wearing a black shirt out on a hot day. Think of all the energy for you, which is heat, that you're having to deal with because of you're not doing anything with it. Like that energy is not being used to do work. So we're going to just add that if it's not, so if a wavelength is not absorbed to do work, that energy is still there, and it's going to be released as heat and or light. And a lot of times that's fluorescence, which is just the ability to send that wavelength out in a pattern that's a color. So we can write that down. So it's fluorescence. I don't know if you can see that. There's supposed to be C. Okay, so it's fluorescence. F-L-U-O-R-E-S-C-E-N-C-E. Okay, so that's done. And that's all of the stuff that has to do with light. So if I had to think about what's important, I would think about this statement here. Short wavelengths have more energy. So if I go over here and I look, short literally is measurable. So 380 nanometers is shorter than 750. So we can come over here, and this is shorter, right? Equals more energy relative to longer, because I mean 750 is longer than 380, which equals less energy. The more energy you have, the more ability you have to do work, and it all comes from how long the wavelength is. Whatever is reflected back to you is what you see. Pigments reflect that color back to you. And I will show you real quickly. Good grief. Yes. So this is both the absorption and the action spectrums. And so what you can see is they have a way to measure. So the absorption will be all of these, and they're telling you. Chlorophyll A is the one in blue. So like we said, it goes from 400 to about, what did we say? Through 5, what is it? No, 450. I was going to say, that didn't look like it. To about 450. Then there's not much action that it gives you. And then it picks back over here up at 650 and goes to about 700. But the action spectrum of all of them is the summation of all of these absorption spectra. So you would have chlorophyll A has its part, big part, but beta carotene's like, hello, I'm a carotenoid, I'm helping, and I expand this over farther than you would get, and chlorophyll B also expands it. So that's what the difference is. So the action's bigger, broader than any one pigment by itself because it's a summation. I feel like I've run a marathon. I know you do too. But I think you're wonderful. Thank you for being patient with me.